Yeah, you, Hello. Can people hear me? Great. Hello, my name is Kai-Mei Fu, and I'm an experimental physicist in the University of Washington Physics Department here, and I've been given the honor of introducing tonight's guest, David Wineland. I'd first like to thank everyone for joining us for our fourth Frontiers in Physics public lecture. As you may know, this series was started to provide our community inspiring free lectures on the latest advances in physics given by the people who directly contributed to these advances. The broad range of topics that we have heard over the past 2 years mirror the broad impact that physics has on how we view the world and also how we impact and affect our world. In our last lecture, we learned from Dr. John Preskill how the spooky and non-intuitive nature of quantum mechanics may lead to unprecedented computational power. And in the spring, stay tuned, we will hear from leading particle theorist Dr. Lisa Randall, who's well known for her work showing that extra dimensions can help solve some of the fundamental problems in physics. Today, we are excited to hear from Dr. David Wineland, our third Nobel laureate in this series, on his contributions to the measurement of time. Before introducing David, I would like to first take a moment to thank Dr. Patrick O'Hara and his wife, Dr. Katerina Randolph, who unfortunately can't be with us here tonight. It was their vision to start this series. They approached our department thinking that what our community needed was a public lecture series, bringing the public to learn about what's happening in physics today. And because of their generosity, it has become a reality. I would also like to thank Phil Ekstrom, who wrote the program that you all now have on a short history of timekeeping. Phil was a PhD student of Hans Dehmelt and overlapped with David Wineland during his time as a postdoc at the University of Washington. On that note, I would actually also like to add that if you're interested in getting involved in the physics department, we would love to hear from you. There's contact information on the back of your program. So getting involved with physics can be attending a lecture. It can be getting added to an email list so you can hear about all the colloquium that we have and other public and outreach events that we have going on. And also it can be helping to support our students, individual research projects, and outreach events that we have for our community. And so now on to the introduction. David Wineland, he grew up in California and graduated from Berkeley with a bachelor's degree in physics. He then completed his PhD with Norman Ramsey at Harvard before joining us at the University of Washington for his postdoctoral work with our own Nobel laureate Hans Dehmelt. This was before Norman Ramsey and Hans Dehmelt would later be awarded the 1989 Nobel Prize in Physics. And so if you could say one thing, you could say that David really knew how to choose an advisor, since both of his advisors were chosen. After leaving University of Washington, Dr. Wineland joined the now National Institutes of Standards and Technologies, and for the next decade, pioneered precision techniques to measure and control individual atoms. The main motivation for this work was precision timekeeping. But in 1995, there was a theoretical proposal by Sirac and Zoller on a new way to process information, quantum information processing of ions. And because of this very fundamental work on clocks that he had been performing, within months of that proposal, he was able to demonstrate a quantum gate with single or two ions. This seminal work, this high precision control, which led to his work in clocks and quantum information processing, was honored in 2012 with the Nobel Prize. As some of you know, David Wineland spent his postdoc here at University of Washington with Hans Dehmelt. And Hans Dehmelt passed away this past year. It is fitting that we're able to hear today about new scientific results that, in part, were influenced by Demel's work. Just as one day in the future we'll hear of discoveries that are enabled by David Wineland's work, which he'll discuss today. Thanks.
Well, thanks for the introduction, Kaime. And first of all, thanks for all of you coming. I mean, one of the nice things about giving this kind of lecture is to see the large scale interest from the public. And so I can't teach you everything about what we do, but I hope to give you an impression of what we do and some of the simple ideas that will hopefully come across. So you can see my outline there, what I'll talk about. And, let's see. Oh, I know. Really, I'm an experimentalist, but I got to turn on the on switch. Okay, here we go. Oops. Well, that didn't work out too well. Okay, here we go. So I can start by saying, well, what's the use of clocks? And throughout history, it's been primarily for navigation, and that application is still true today. So just going back on a little bit of time, I'm not a sailor, but any sailor will know what I'm talking about here. And the basic idea is for navigation is you want to determine your latitude and longitude and therefore your position on the Earth. And the easy part is the latitude, where the basic idea is if there's some distant star, in this case the North Star, if you measure the angle of the direction of the star relative to the level, the tangent of the Earth, you can easily determine the latitude that you're at. The harder part is longitude, and there you need time, and the simple reason is because the Earth is rotating. So the principle is the same. You're going to be looking at some distant star that's relatively speaking fixed in your view, and you determine where you are by measuring the angle between the star and the tangent on Earth where you are. The problem is because the Earth is rotating, you need to know time to know exactly what the angle, how the angle corresponds to your position and longitude. And I won't go through the simple math. The scientists out there will understand this. But the idea is, what are the errors due to the error in time? And just a simple example I show here, and the idea is that a relative distance, say an error given by the error in the angle can be related to the error in time. And so this section of distance in latitude is given by this simple formula here. And so the idea, of course, this angle is changing in time, and there's an imprecision given by the imprecision in time. So in this simple expression, we're rotating it once per day. The radius of the Earth is about 4,000 miles. And so for an error of 1 second in time, that gives a relative error in latitude position of about a half a kilometer. And so just a little history. There was, of course, sailors going back many centuries relied on time to be able to navigate. And there was several incidents in the early 1700s where the Brits lost ships at sea, and so the British Parliament decided to sponsor a prize, the so-called Longitude Act, and the prize was given to someone who could demonstrate a clock which would allow navigation to about 30 nautical miles, which translated to an error in time of about 2 minutes. And there's a famous story, many of you may have read the book, there's a couple of good books about this. John Harrison, who came up with a clock. It was actually like a large pocket watch. It was a mechanical clock that he came up with, and he was able to demonstrate that it was within this within the errors that were required by this to win this prize. And part of the story is, you know, the Parliament, you know, they wouldn't give him his money, and I think it was a couple decades before the king stepped in and got him his money, and then I think he died a year later or something like that. But anyway, it's a good story. There's a couple of good books. It's a good story to read. But of course, these days, the way we navigate is via GPS. We kind of take it for granted these days, and the precisions can be much higher. And the basic idea there is that to give you the idea, you want to determine your distance from some satellite. And I won't go through the math, but the basic idea is that because clocks are so precise, basically you can think of a simple protocol. It's a little bit more complicated than this, but if you agree that the satellite is that, first of all, your clocks have to be synchronized, and if you establish a protocol, say, where the satellite emits a pulse of radiation every second tick, then there'll be delay because of the speed of light before it reaches you. And so, to give you an idea of the precisions that are involved, for an error in time of about a nanoseconds, 10 to the minus 9 seconds, that gives an error in distance here of about 30 centimeters. And where clocks come in is basically we'd like the clocks to be autonomous, at least over extended periods. And so if we have an error of a nanosecond over one day, that corresponds to a relative frequency uncertainty of the clocks of about 1 part in 10 to the 14. And these are the kind of numbers we're able to reach today. Of course, it's a little bit more complicated to get three-dimensional navigation. There's a network of satellites, and in fact, the system, there's enough redundancy in the system that the satellites can not only know their position, but the clocks, can be synchronized together. So we can get three-dimensional position at this level of precision. So anyway, a bit about clocks. I think most physicists' notion about time is very similar to the non-scientists. It's a sort of a measure of the progression of events. And the basic idea of making a clock then is we have some periodic event generator and a counter, and with that then we can generate time. And traditional event generators are, of course, the rotation of the Earth, and also later the pendulum clocks were invented, and the precision was quite a bit better than given by the rotation of the Earth. But that's basically it. So these days, though, we think of using oscillations in atoms, and a simple picture you can think about is, say, an electron orbiting around the nucleus. That's a pretty good picture. Quantum mechanically, it's a little bit more complicated. What we think about is say an electron orbiting around the nucleus. The quantum mechanics tells us that the electron is not. It can't be. Its position can't be precisely defined. But nevertheless, there's a very precise timing of the orbit of the electron around the nucleus. And this picture over here is meant to show a dipole where the electron is actually oscillating through the nucleus. But the basic idea then is that we establish this oscillation in the atom, and the key part is that, as the early quantum mechanics told us, is that atoms don't exist in any arbitrary kinetic energy state. There's a certain discrete energy levels associated with the electron orbiting around the nucleus. And the basic idea is that the frequency of the oscillation is then given by the energy difference between these two quantum states divided by Planck's constant. So one simple mode of using these oscillations is called a maser or a laser, and we're more familiar with the laser. Actually, the first devices that operate on this principle were called masers. M stands for microwave versus light, and the simple picture is we have atoms that we stick them inside of a cavity which contains the radiation. We sample a little bit of that, and then we have a counter to generate time. So a little bit of personal history. I was a graduate student at Harvard with Norman Ramsey, who's right here. And Norman and his colleague Daniel Kleppner had recently invented and demonstrated the first hydrogen masers. So the basic idea of what I showed on the previous slide. So this was the group in 1967. I started in 1965. That's me getting close to the boss there, you see. So, anyway, so when Norman wanted to have precise measurements of all the hydrogen isotopes, the maser oscillation frequency of all the isotopes. So my project turned out to be to make a maser based on the deuterium isotope, and the experiment wasn't anything very astounding, but it taught me a lot of nice techniques in atomic physics, and so this was the result of my thesis here. I'm probably the only one that has this number memorized, but anyway. So, but certainly what came into play all through my career, and the things I'll talk about that we did later, was basically the name of the game here is although the atoms are inside this cavity, there's various perturbations that they can undergo, and so that one of the requirements is to precisely control the environment they're in. The other thing is that as they were radiating, the atoms live in so-called superposition states where they're radiating, and these superposition states are actually rather long on the grand scale of superpositions. They lasted about a second. So that I give you, there's another mode of operation. I showed you the laser or maser mode of operation of a clock, and the other is where we actually say again, here's the energy structure, and what we do in this case is we would apply radiations to atoms, say in a cell here, and basically we just look for the condition where the atoms absorb the radiation maximally. Then we know that the frequency of this oscillator is equal to the frequency given by the energy level separation. So a recipe for an atomic clock is very simple. The basic idea is we have some oscillator here which supplies radiation, and in the previous example we look for the condition of this, the frequency of this oscillator where the absorption is maximum. And we can think of it, I won't describe the electronics here, but we can think of a simple servo system that feeds back, that forces the oscillator frequency to be equal to the frequency given by the energy difference. And when we reach that condition, we just count cycles of the oscillator. Now, in fact, there's a little subtlety here is that we get a curve that registers the absorption. It's not infinitely narrow. There's one of the reasons it's not is that the atoms in the excited state will decay, and that limits the resolution we have with this absorption feature, we say. And so the only other ingredient to actually the way we work it is if we sit right on the top, we're not very sensitive to small changes. With the top of this curve is flat, basically. So the only difference that we do is we do it in a stepwise fashion where we'll first probe on this, probe on the left side of this absorption feature, and then we'll step over to the other side and a probe on that side. And when we get an equal response, then we know that the mean of those two frequencies is equal to the resonance frequency. So that's the only wrinkle beyond what I said before, but it's actually no more complicated than that. So again, but a bit more common mode of operation, that was sort of for looking for continuous absorption. The way most clocks work is just slightly different. We basically start the atom in the lowest energy level, and then we apply radiation for a short time, and that's basically the same idea is that when the radiation frequency of the oscillator is equal to the resonance frequency of the atom given by this expression here, then we know we're on resonance. And of course we step from side to side of the absorption feature. And basically then to measure this absorption, ideally we could look at the maximum absorption probability, but of course we step from side to side of the line. So it's just a slight difference from what I said before. So, well, why atomic clocks? And there's a couple of strong reasons why atoms are nice. And in this view graph, I'm going to compare to the pendulum clock, which actually is still good pendulums are extremely good, almost as good as quartz crystals. But you can think of quartz crystals like they have the same conditions, or some of the same conditions we have to worry about. But let's take the pendulum clock. So the frequency of a pendulum clock, as students in physics learn early in their careers, is given by this simple formula where this is the acceleration of gravity and this is the length of the pendulum bob. And so what are the sensitivities? What can cause the frequency of the oscillation to change? And one is, say, temperature. The temperature is not precisely controlled and can be fluctuating. So what happens in this example of the pendulum is that most suspension rods are a metal usually, and of course with temperature changes the metals usually expand and contract as the temperature cools. And I won't go through the details of this simple derivation, but the basic idea is that even with materials of very low expansion coefficients, so this represents the fractional change in the length of the pendulum versus temperature, we get to we work through this simple expression here, and we get to sensitivity of expressed fractionally of about a part in 10 to the 8th per degree C, frequency change of the pendulum clock. Now, with atoms, what's nice is that we still have to worry about temperature effects, and actually one of the more interesting one is due to Einstein, and that is the fact that typically in this container that we're holding the atoms aren't at rest, they're moving around. And what Einstein told us was that with two frames of reference that move relative to each other, time runs at a different rate. It's not just as simple as saying the clock here based on the atoms runs at a different rate. Actually, time runs at a different rate. So this was an amazing revelation that changed our notion about nature, and it was due to Einstein. So anyway, but to give you an idea of the size of the effect, we do have to worry about this in our high precision clocks. And again, I won't go through the simple math here, but for a cesium atom, which has a mass of 133 mass units, the frequency of the oscillation will change due to this relativistic time dilation, and the fractional change per degree C is about a part in 10 to the 5th. So many orders of magnitude smaller sensitivity to temperature changes than this pendulum. And there's a simple, of course, we're more familiar these days with quartz crystals in our watches, but also in that case, the temperature sensitivity of those is quite a bit larger than what we can get with atoms. Okay, so the other thing we have to think about is if we make different if we realize different versions of the clock, how reproducible are they? And of course, with a pendulum clock, we have manufacturing tolerances to worry about. The length of this pendulum for different realizations can be different, which gives a different oscillation frequency. Of course, there can be wear. The pendulum, the bearing on the pendulum may wear a little bit, which will effectively lengthen the distance of the length of the pendulum bob. And of course, it depends on the local value of gravity, which can change around the world and also fluctuates with earth tides and things like that. So the nice thing about atoms is that all atoms of a particular kind, as far as we know, so far they're absolutely identical. So if we can agree on an atom whose frequency we measure, then we, in principle, can get exactly the same frequency within these environmental perturbations that we have to worry about. And the other thing is atoms don't wear out. I mean, we can take the same atom and repeat this absorption process in principle an infinite amount of times, and they preserve their properties throughout. So these days, actually starting the first cesium clocks, which measured the whole so-called hyperfine transition at a frequency of about 9 billion cycles per second. It was developed in the early 50s, and by the mid-50s, by international agreement, we used that to the oscillations of the cesium hyperfine transition to define the second. And this definition still holds true today. What I'm going to show you is at least the performance of the clocks we can make now are better than we can realize with the cesium, measuring the cesium transition. Of course, cesium was always getting better through the decades, so it was like a moving target, but we finally were able to overtake the performance about 10 years ago. So why optical clocks? And one of the simple reasons is that the oscillation frequencies of electrons around the nucleus are much higher than this so-called hyperfine transition. In this case, compared to cesium, the oscillations of a typical optical oscillation are about 100,000 times faster than the oscillations of the cesium clock. And so what that means very simply is we get more ticks in any given interval of time, say the second, so we can define that interval divide that interval of time into finer and finer increments. So that's the simple reason we want to think about high frequency. The other thing is that for certain transitions, and I'll say a little bit more about that in a minute, these transitions, the frequency over which they absorb can be extremely narrow compared to the actual frequency. So we get a very high relative precision. For most of the cases I'll talk about, this width then, which is not infinitely narrow, is given by the lifetime of the upper state in the transition. So is it a new idea? And the answer is no. And in fact, a colleague at NIST in Boulder, he did some research and he published this paper in the early 70s, and he dug up a text from Thomson, Lord Kelvin, and his colleague Peter Tate, and they in their paper they acknowledged this idea was due to Maxwell, the inventor of the formalism of electromagnetism a long time ago. But anyway, they wrote this couple of sentences here, and their idea was basically what we're talking about with these atomic clocks, and they basically said, well, there's recent discoveries that is seeing the different wavelengths of emission of different atoms. They said so they had the idea of you could read here, but atoms such as hydrogen or sodium, which are relatively available in nearly infinite numbers. They're alike in every physical property. So this is what I was saying. They're absolutely identical. So they had that idea. And so they were actually thinking about when they say vibration of sodium particles, this was actually optical oscillations that we were thinking about. So the basic idea here has been around for an extremely long time, and of course it's the technology that had to catch up to be able to realize this idea. Actually, one interesting thing in this same paragraph, they say this oscillation of these modes is known to be absolutely independent of its position in the universe. And they can be excused because this was before Einstein came along and said, no, that the rate of time is not absolute. But anyway, they certainly had the basic idea many, many years ago. So anyway, after my graduate career, I came to the University of Washington, and I worked with Hans Steenmalt, and his main interests, I was mostly attracted by, I'll say this in a minute, but anyway, he and his colleagues had done spectroscopy on, it was helium ions, and I was interested by that and potentially the application of atomic clocks. But anyway, Hans wanted to focus on experiment to measure the electromagnetic moment, and the basic idea there is an electron, in addition to its charge, has the property that behaves also like a little magnet. And the reason this experiment was so important was that the theory of quantum electrodynamics can predict the value of this magnetic moment to a precision of about uncertainty of about a part in 10 to the 12th. And so this experiment was very important because eventually it was able to measure this precision to about that level. And that's a whole separate story, but anyway, two things to say here is that actually Bob Van Dyke, who's in the front row down here, was the person that actually led the experiment starting at the time I was here. And I didn't stay around for the actual important measurements. So these first very precise measurements were done by Bob Van Dyke and other colleagues here at University of Washington. Another thing to say is that because Hans was developing these techniques to confine, in this case, electrons, and previously the ions, he shared the Nobel Prize with Wolfgang Paul, who invented a slightly different kind of ion trap, we say, that we actually use for our clock experiments. And I won't say anything very much about how the trap works. You can see this electrode structure that I've drawn in cartoon form that looks pretty much like this. For the non-technical people in the audience, a very simple analogy is it's like this. When we apply electric fields to this electrode structure, we create for a single ion, say in the trap, it's like a marble in a bowl. We create a so-called harmonic potential, but this analogy to a marble in a bowl that rolls back and forth is actually very good. So the other thing was that I mentioned that I was attracted earlier on, actually, Hans and his colleagues, one being Norval Fortson, who was a postdoc before my time. He was actually a Ramsey student before my time too, but he came to work for Hans, and they were measuring the same kind of so-called hyperfine structure in helium, and this was the resolution was very high, so this in some sense people gave the ideas, and I was certainly interested in how these ideas might be applied for atomic clocks. So what I'm going to show here is focus on one experiment we've done in our lab, and I have to say, and I'll repeat it later, that this kind of work goes on in many labs throughout the world, and I'm going to focus on just this example of how we used a Mercury ion to realize an atomic clock. And I should also say we did many different kinds of experiments with these ions, but this project here, I'm making a frequency standard out of the Mercury ion, was led by Jim Berquist in our group. So I've been a colleague of Jim for the last 42 years, and so we've done a lot of things together. Anyway, so the basic idea here is, again, coming back to the simple picture I mentioned before, is that basically we start the atom in the ground state, and then we apply radiation during this for a short amount of time, and then the idea is we measure whether the ion has made the transition up to the excited state, and we look for the condition where it does with the frequency of the laser where it makes that transition with highest probability. This transition is actually in the ultraviolet, which is a bit of a technical problem, but we can make radiation at that frequency. Anyway, the idea, one of the issues is how do we detect when this atom has made the transition? So, well, let me first say these experiments we've done for quite a while have been just with a single atomic ion in the trap, and so why do we focus on one ion? And there's one reason with Mercury. It turns out the upper level in the Mercury ion, it kind of has the shape of the electron cloud around it is kind of like a football, and it turns out that the inhomogeneous electric fields on one ion, as seen by the other ion, interact with this football-shaped charge distribution and can give a frequency shift. And it's fairly large compared to the resolution we're trying to achieve. So that's one of the reasons, at least our experiments, mostly up till now, have used just one single ion. In any case, the way we detect is to look at another transition, and this one I should have mentioned here. The lifetime of the upper state in this Mercury ion for this clock transition is about 1/10 of a second, which gives this very high resolution we can achieve. So the way we detect our ions is or at least first of all to even identify that they're in the trap, is we use another transition in Mercury, and this one can scatter photons at a very, very high rate, on the order almost on the several hundred megahertz per scatter rate. And the nice thing about that is we can not only identify atoms, and in fact in these experiments we can with a camera that works in the ultraviolet, we can actually make pictures of our single ions. And actually Damilton and his colleagues, this was after I left, but they also were working on single ion experiments, and most of the ions, because there's one electron removed to be able to excite the next electron, the transitions are out of the visible spectrum in the ultraviolet. But there's a couple ions, and one of those is barium, and so Damilton and his colleagues, they actually made fluorescence of or could see it make an experiment like this, and the light that was scattered was in the blue part of the spectrum, but in these experiments you can actually see with your eye a single atom, which is pretty amazing when you think about it. It kind of looks like a faint star, but you can actually see it with your eye. So one of the issues we had to think about is that, in fact, in the early experiments on helium that I described that had been done by Norville Fortson and Damilton and their colleagues, was that the atoms were actually moving fairly quickly in this, bouncing around fairly quickly inside this trap. And so one of the limitations was this time dilation shift that Einstein told us about. So one of the messages from that was it'd be nice to have a way to slow down the motion of the ions to cool them, basically. And this was, again, to suppress this time dilation effect. So the way the simple form of laser cooling works is the following. And this, and actually, when I was here as a postdoc with Damo, we published a little paper on how this would work, and at the same time, independently, two colleagues, Ted Hench and Art Shallow, who later also won Nobel Prizes. Anyway, we had basically the same idea, and the idea, if you'll bear with me a little bit, it's not too complicated, and the basic idea is that I've already told you that atoms, rather than the energy of, say, the electrons, rather than existing in a continuous spectrum of energy states, they're confined, the energy is confined to discrete energies. So that's a key part of this. And then, as I said, just for a clock, I haven't said much about the motion, but if the atoms are absorbed, then when the laser is tuned to this so-called resonance frequency given by the energy difference, then they absorb maximally at that condition. Now, of course, what we have to think about is, in general, even though the atoms are confined in this trap, we say that they're moving around, say, with some amount of kinetic energy. And the idea is that if the atom is, say, moving against the laser beam, one thing we have to worry about is the so-called first-order Doppler shift. And the common example of that we all experience is if, say, in my day, the example was a train that would go by you, and the train whistle, as it approached you, would be higher pitched than it was receding from you. And of course, the same effect with a car going by or a motorcycle going by, that you hear this change in the pitch of the sound, and the same idea applies to light. So the idea here is that when the atom is moving against the photons from this laser beam, they actually absorb, but not the frequency they absorb at with their rest, but the frequency they absorb at is shifted by the velocity divided by the speed of light. And we can take advantage of that, because the idea is then what we do is a laser comes in from this side, and we tune the frequency lower than the frequency it would absorb at rest. And the idea is when the atoms move into this resonance condition here, the atoms will absorb the light, and when they absorb the photon, they get a momentum kick, which in this case is against their motion. And then when they re-radiate, generally they do it in all directions. So on average, every time they absorb and re-emit a photon, the momentum is reduced by the momentum of the photon. And so we can repeat this process, do many scattering events, which gives the slowing process, which allows us to cool the atoms down. And so that's what I just said. And so this has become a standard technique now in all atomic clocks, because the precisions are high enough that if the atoms are at room temperature, the shift is just too big from this time dilation effect. So we have to invoke this cooling idea. So anyway, when I did a little bit of personal history, is that when after my postdoc position in Demont's lab, I got a position at what was then called the National Bureau of Standards, now called the National Institute of Standards and Technology. And my first job there, when I went there, was there was a cesium beam clock. That's what this is here. Basically, cesium atoms are made to travel down this tube, which has a vacuum, and that make a stream of cesium atoms. And when they go down this tube, we measure the radiation of this so-called hyperfine transition. But anyway, my group leader at that time, the person that hired me, had a vision for NIST that we should be doing more research. So luckily, he got us some money to try this idea of laser cooling. And sort of an interesting personal aside was the fact that after Demolt and I had this idea, and Demolt had taken a sabbatical. It was actually I left, and he went to work in Peter Toshek's lab. He was then in Heidelberg, and I knew they were going to try to demonstrate this cooling, but we got some money at NIST to try this experiment. And so they didn't know about our experiment, but I knew they were trying to do this, so we were racing at least. So what's interesting is basically without any, I knew they were working on it, but I had no idea where they were in terms of their progress. But interesting, the papers on these first demonstrations were published about the same time. You can see that ours was published a little bit earlier, but to be fair, if you look at the dates these were received at the journal, they beat us by one day. So anyway, as most of you know, I think, These experiments are relatively long term, and if you do it within a few months of each other, it's certainly a tie. So anyway, both groups got credit for doing this at the same time, but this was amazing near coincidence here. Okay, I'll say a little bit more about this. So I have already alluded to this. For this Mercury ion optical clock, we're going to use this transition here in the ultraviolet at about 282 nanometers. How do we measure the transition? So one way we describe this process, again, we start the atom in the ground state, we apply this radiation for a little while, and then we make what's called a superposition state. So the atom this is kind of a standard notation for wave functions, but the wave function in this case, after that we apply this radiation, is that the atom is, we say, a superposition of the lower state and the first excited state. And the one nice thing, we have a very good way of measuring when the atom makes the transition, and it's basically, it's the idea of the following. When we turn on this other laser, then we tend to, this superposition state that we made, it can, we say, collapse into either the ground state or the excited state, and it does it with a probability that's related to these coefficients in front of these components of the wave function. But the key idea is that when the atom, if we suppose we try to drive this transition, and suppose that the frequency of the laser is a bit off, then the atom remains in the ground state. And we can tell when that happens, because then when we turn on this laser here, we're going to see scattering, like at the picture I showed, and we can pick a bit of that up in a say, a photomultiplier, some detector. On the other hand, if we're close to resonance, then there's a high probability when we turn on this, pardon me, this laser here, that the atom will actually collapse into the upper state. And when that happens, we don't see any scattered light when we turn on this laser here. So the nice thing is that we can easily discriminate which state the atom has been detected in. So for example, this shows, this data here is, we were causing transitions, but the data that we took, we would average the fluorescence for about a millisecond, but you can easily see that if we put a discriminator here, we can tell with essentially 100% efficiency what level the atom is measured to be in. There's a lot of details in this, but anyway, some of the interesting ones in this Mercury ion experiment was basically the electrode structure I showed in cartoon form. It's a little hard to see here, but that's this same structure that I showed in the cartoon. In this case, one of the unfortunate things is that with Mercury, the way we would create the ions is we just leak in a little bit of mercury vapor, and then in those days, we had a very crude experiment. We would make a crude electron beam make a homemade filament and stream electrons through that ring electrode in the trap. And then when the neutral mercury atoms were inside, occasionally one would be ionized by this electron beam, and when that would happen, the ion would be trapped. But one of the problems we had was that it turns out mercury, if you leak it into a metal vacuum system, which you can see that this is the container without the lid, is that the mercury, it turns out, when you leak it into a vacuum system like that, what it does is it amalgamates with copper. But on the other, so what it basically diffuses into the copper. But the problem is there's always, even if we try to pump all the mercury away, the mercury is effusing out of the vacuum. And the problem that made was, it turns out that when the mercury ions were in the excited state, if they collided with a neutral mercury atom in the background, they would radiatively associate, we'd say, and it would make a mercury molecule, a dimer, a two-atom molecule. And basically that was the end of our atomic ion qubits, or ion for the clock. And so it was just a horribly annoying problem because we'd get all the lasers tuned up, and then after 10 minutes, this collision process would happen, and we'd have to reload the ion and tune everything up again. So basically, we just hit it with a sledgehammer, and that is, we put our ion trap in its enclosure. We attached it to a liquid helium reservoir, and basically the liquid helium temperature under normal conditions is at about 4 Kelvin absolute. So basically, everything freezes out except for maybe some helium, but helium's not a problem. So literally, we went from storage times. We could keep the ion earlier for only about 10 minutes, and we could literally increase the lifetime to about 6 months, and that was just due to that we'd do something stupid which would kick the ion out. But there's other advantages to going to low temperature. One is that I've already alluded to, we basically freeze out most of the background gas, so the collisions are almost reduced to nothing. Another subtle thing is that it turns out the clocks are perturbed by thermal radiation, so-called black body radiation. And I was always, when we're first thinking about this, it turns out the thermal radiation in the room, the electric fields due to that radiation are not insignificant. They're about 10 volts per centimeter, so they're actually fairly strong fields, and we're all bathed in this radiation. Anyway, this radiation could shift the frequency of the clock, and so it'd be nice to reduce that, and one way to do it is to put an atom in at a very cold temperature. Okay, so there's other issues. Now, the way I mentioned that the absorption range of this mercury ion, it would be about 1 hertz, 1 cycle per second wide out of about 1 billion cycles per second. So it gave very high resolution, but one of the problems we had going into this, everybody had, was the laser, although we knew how this should work, the lasers were not stable enough. In other words, the wavelength, the frequency and wavelength of the radiation would fluctuate around. So the standard technique that people used for many decades, and it's still the way people do these experiments, is basically we form a resonant cavity with 2 mirrors, and what we do is we shine our laser radiation in there, and for the physics students here, they know this problem is basically the cavity will only will build up radiation and only transmit radiation through when there's an integer number of half wavelengths of this radiation given by the distance between that fit inside the distance spanned by these two mirrors. And so basically we can, although there's many frequencies that can happen, we basically stabilize our lasers to one of these transmission conditions, and then the stability is governed just by how well we can control the distance between the mirrors. And actually this has a lot of similarities. This last year with the big splash was in the last year or two was to be able to detect gravity waves by looking at the oscillations of these mirrors, and we're not nearly as sensitive as those instruments, but the idea is very much the same. We can stabilize our lasers as long as the spacing between these mirrors is very precise. So anyway, Jim Berquist and I had the idea, a very simple idea, to get rid of mechanical vibrations, as he basically supported what this cartoon is meant to show. Here's one mirror. The other mirror is hidden, but there's a glass spacer here that's very rigid and provides a rigid distance between the ends of these mirrors. One thing, again, it's no comparison to the sensitivity of the gravity wave detectors, but what I always found interesting was that when we set this down on the floor to tune up the optics on the small optical table, we'd always see some noise very close to the center frequency where the laser would be locked to this resonance given by the spacing. And we always see some noise on the side at much less than a hertz, about 1/7 of a hertz. And that turns out to be the waves crashing on the beach in California. That gives this broad sort of noise spectrum at 1/7 of a hertz. Anyway, the state of the art these days, we're still bothered by vibration, and we're now affected by the same things that in part limit the detection sensitivity of the gravity wave detectors. That we still have to worry about mechanical vibrations, but what it comes down to now is we have to worry about the spacing of the mirrors, but the main thing we're left with is actually the coatings on the mirrors that give the reflectivity. They're also mechanical systems. They vibrate and they give some noise, which limits how well we can stabilize, in our case, the lasers to this cavity. Okay, well, coming back, I'm just going to summarize the many years of work. And first of all, the fact that we're trapping the ions, on average, their average velocity is 0, so we get rid of what's called this first-order Doppler effect. What we call the second-order Doppler shift or time dilation is suppressed highly by this idea of laser cooling. And I've already mentioned we suppress several other effects by going to low temperature in this apparatus. So the one thing that we felt proud about, and it's mainly due to Jim Berquist, was that we had been chasing the performance of cesium for decades, and so in about 2006, then this was the first clock that could demonstrate that an optical clock was actually better in terms of performance than the cesium clocks, and so nowadays. All the standards labs, for sure, we've all gone to optical clocks. Some of the other ions that people are using, we're actually using aluminum these days. It's a bit better performance than mercury, but there's many choices. And of course, there's many neutral atom choices. One of the interesting possibilities that people are looking towards is the thorium nucleus has a nuclear transition, which by coincidence, there are energy levels which are separated by close to an optical transition. And as time evolves, it appears it's pretty far in the ultraviolet, but nevertheless, this is an interesting idea rather than using atomic transitions to be able to use nuclear transitions. So let me just come back to these so-called systematic effects, the environmental effects that cause frequency shifts. I've told you about the first-order Doppler shift where because the atom is trapped, its velocity goes to 0, and then there's this so-called time dilation or second-order Doppler shift. Now, I lied to you a little bit. Although the atom is trapped, and it's true that its average velocity goes to 0, one thing we have to worry about is that the laser we have an optical table that the laser sits on, and then our trap is, say, at the other end of the optical table. And what we have to worry about is that the temperature in the lab changes, the table is shrinking and contracting a little bit. And with the velocities we're sensitive to at the level of precision we're at now are about 0.3 of a nanometer per second. So we have to stabilize the distance between the laser and the clock the clock atom in this trap. And what we do there is we actually borrowed a technique from satellite ranging, where basically the satellite ranging is done by sending a signal out, effectively reflecting it off the satellite. And the signal that comes back is shifted by the Doppler shift by basically twice the first-order Doppler shift. And from that, we can measure the velocity, in that case of the spacecraft. We do the same thing here, only the velocities are quite a bit smaller than the velocity of a satellite, or rather, in this case, a deep space probe that's but anyway, we use exactly the same technique to subtract out this Doppler shift. Now, I've also talked about the time dilation shift, this famous so-called twin paradox by Einstein, and we suppress that with laser cooling. There's another effect which is also, well, anyway, so the net result of our experiment so far is we're down a fractional precision, which is how we characterize all the clocks, because we can, doing it that way, it's only the real measure of the performance is the relative precision. So we're down to a level of about 8 parts in 10 to the 18 with these experiments. So one of the effects we have to worry about is the so-called, again due to Einstein, the so-called gravitational potential redshift. And in addition to the time dilation shift due to movement of the ions, Einstein also showed us that clocks run at different rates in different gravitational potentials. And so one example I can give you is that suppose you had a twin brother or sister and you were separated at birth, and suppose your twin lived in Boulder, Colorado, where we are, about a mile above sea level, and you lived at sea level. It turns out that there is an effect, but it's nothing to really worry about too much. And in fact, it's after 80 years, your twin will be about a millisecond older than you are due to this potential. So it's a very small effect. Nevertheless, we can see this effect. So kind of as more of a stunt, but kind of a fun thing to do is to demonstrate this effect on a kind of a more everyday scale. So this is so just to kind of show this effect. This is our optical clock. This one is based on aluminum, but the principles are very much the same of what I described for Mercury. And so obviously this is not the one you wear on your wrist yet, but nevertheless we made a clock like this in one lab. In an adjacent lab, we had another clock based on aluminum, which, as far as we could tell, was identical. Anyway, we measured the ratio of the frequencies of those two clocks, and it was about out here to, I forget how many, on the order of 17 digits anyway, that they were running at the same frequency. And then just as a demonstration, James Chow, who is running this experiment, is basically, you can see he's put some jacks under the table here, and he raises the table up by about a foot, 33 centimeters, and we could actually see that we could resolve this so-called gravitational potential redshift. So the precisions now are such that we do have to worry about these very small effects, including this gravitational potential redshift. So where are we at these days? So I showed the number we achieved, this fractional precision that is taking account of all the environmental effects. So we actually had the lead for a few years, but now there's always been many other groups working on that. And so these results have been superseded more recently by, first of all, we had some colleagues in basically the German version of NIST, where they've made a clock based on ytterbium ions, and the precision in their clock is a little more than a factor of 2 smaller than in ours. The other thing I haven't talked about, but it's important, is that I've been talking about single ions, and for the reason I mentioned, but we do want to scale up the number to larger numbers, and it's simply we get more signal with more ions, and so we can improve the time it takes to reach a measurement precision. So we're making traps that don't look the same, but basically we make strings of ions and therefore increase the numbers that we can play with. And also there have been a number of experiments done with neutral atoms, and they don't use the same kind of traps, but they're able to make traps by using laser beams, and kind of a cartoon version in 2 dimensions. It's kind of like a egg crate that can hold individual atoms, and they can do this in 3 dimensions. And so this work first started, the first high precision measurements were done by a group of Katori in Japan, but the leader in more recent years has been Jun Yi in the group at JILA, and they're down now to where the so-called systematic precision is down about 4 times lower than we're able to do. And the other thing is they can hold quite a few thousand atoms in their so-called egg crate structures, so they can much more quickly reach high precision than we can with our single line. So we have some catching up to do now. But anyway, so the best precisions are very close to a part in 10 to the 18th. And just another thing to compare back to this gravitational potential redshift, the shift due to this gravitational potential redshift is about 1 part in 10 to the 18 for a centimeter rise in position. So we're getting down to these very sensitive values. Actually, coming back to this, one problem we have is that if we because of this gravitational potential redshift, one of the problems we have is that in order to compare two clocks, the problem is we can make measurement comparisons between clocks, say one at sea level and one in Boulder, Colorado. The problem is we're limited in precision because we don't know the height of Boulder in terms of this gravitational potential redshift to only about 30 centimeters. So in fact, with these higher precisions, we're limited in precision simply because we don't know the gravitational potential redshift between sea level and Boulder. So the only way we can make precise comparisons of these really accurate clocks is we have to bring them together when we know they're in the same gravitational potential. So this is kind of a headache, right? But of course we tried to take the high road, and so one view is to take these and the future is to take these very accurate clocks and be able to map what's called the geoid, the gravitational potential around the Earth. And I've just mentioned some of the groups. There's many more around the world working both on ions and neutral atoms pursuing these ideas. So what's the future? And so navigation is still one of the main applications. The other is in synchronization. So for example, in network synchronization, timing signals, we need these higher and higher precisions. But nevertheless, we still continue to think about navigation. So at the centimeter scale, you think, well, who really cares? And one application that people talk about is that, for example, a precursor to earthquakes is usually an earthquake is preceded by strain in the earth, meaning two relative locations that might be separated by kilometers. Their relative height compared to the center of the earth will change, and this strain, and eventually the strain will cause the earth to let go. They'll readjust, and so this measuring this strain at this perhaps centimeter level can be maybe not a predictor, but it can be a signal that an earthquake is building up, or the probability of an earthquake is increasing. And so we think about doing this, and I already mentioned this idea of mapping the gravitational potential redshift around the world. There's also a bunch of fun things we can think about doing, and one of the interesting things is if we take clocks that are made on different elements, it turns out that the frequencies that they run at in general depend on different ratios of the fundamental forces, say the so-called strong nuclear forces and electromagnetic forces, which the ratios of the contributions of the frequencies, different basic forces will vary. And so if we measure the frequency ratio of clocks based on two different elements over time, one of the interesting things to think about are the fundamental constants, quotes, that govern the frequency of these transitions, are they changing in time? So we've been able to put limits on that, and this continues on. There's still a lot of motivation to do that. We're always, as a popular game, we're always trying to see deviations of Einstein's theory of general relativity, and so far he's doing just fine, but nevertheless we still try to probe with higher accuracy to see whether there might be variations. And so with that, I'd like to thank the real people doing the group. This is just our group working on these experiments, and there's many groups around the world working on these problems. I'd like want to also acknowledge our laboratory director, Catherine Gebbe, who was laboratory director, meaning the larger group of divisions, like the time and frequency division. And she was very supportive of some of these basic ideas. For example, this idea of laser cooling was, I mean, we just wanted to do it because it would be kind of nifty to demonstrate this effect, but it became very important for clocks, and in fact, it's used in all high accuracy clocks. And she was very supportive of this kind of exploratory work. Unfortunately, she passed away a year or so ago, and but nevertheless, she made a great environment for us. And I'm going to, for those who might know a few people there, I'm going to list people. Actually, how much time? So just, I mean, often, maybe you've seen these things before, but I'm going to say a little bit about the Nobel Prize here. So I think most of you know that. Oops, the prize is. I'll find that later, I hope. Anyway, the prize is announced in around October 10th or so, and I mean the whole thing is very surreal because it is it gets so much attention. But anyway, so they announced the prize in early October, and then the ceremony is actually coming up within days here. I think it's on the 10th of December. Anyway, on the date of Nobel's death, and anyway, so we go there in early December, and this is what's nice. I mean, Stockholm's a very charming city, and actually, even during the dead of winter here, you can see the snow on the ground. It was very cold, but they have these open air markets, and so. I mean, it really, they do a Christmas in a very charming way, I must say. But anyway, actually one thing about this figure, so we get to spend time wandering around a little bit. And one interesting thing about this figure, I mean, Sweden's pretty far north, so this picture was about 3 o'clock in the afternoon, and you can see the sun is already set. So it's getting pretty dark, pretty early there. So anyway, so everything is just way over the top, all these ceremonies. And so this was the award ceremony, and the laureates over several disciplines are all lined up in this first row here. And here's the royal family. And so basically the way the ceremony goes is each person, a little bit is said about the person, and they walk up and receive the award from the king. And so you can see everything is very well organized. We have a rigid uniform, and part of that uniform for us was that we had, of course, had to wear tuxedos, but also we had to wear patent leather shoes, and these patent leather shoes this was a firm carpet, but walking on this carpet is like walking on ice. And the whole time when I was going up to receive my award, I said, just don't fall. Anyway, so I made it through okay. This is me receiving the award from the king. And anyway, after this very fancy ceremony, the royal family had a few people over for dinner. And all this is, I mean, it's just, everything is so much over the top. Actually, one thing I didn't know, Nobel, before going there, is Nobel actually favored the physicists out of the chemists and the other disciplines. And so we were the ones that got to sit with the members of the royal family, at these different events, which was somewhere here in the middle of this table. The other thing to say is that there's about, I think it was like 1,200 people here. And so what you learn is that the Nobel laureates and their guests unfortunately we're only, at these fancy official events, each laureate could only invite 12 people, and there were, I think, 8 of us, I know I'm forgetting, 8 of us that year to receive the prize in these different disciplines. And so that's about 100 guests. And so there was about 1,400 people at this thing. And what you learn is that this is a big deal for not only Swedish society, but officialdom. You know, it's a big deal to go to this event. And it's also nice they invite some students from the local universities. But anyway, it's this very fancy thing. And so the dinner there is, you know, it's extremely well organized. So there was one of these guys here was like a orchestra conductor. So there was, I don't know, 100 or more servers, and they each would serve a few people. But he would wave his wand, and you know, everything would be done in synchrony. And anyway, it was just, as I say, it was really a surreal thing, but of course very, very fun. And I think so. One of the nice things was that the person I shared the award with was Serge Haroche whose lab his lab is in Paris, and I'd gotten to know Serge, 35 years ago. I first knew him through the literature because he done some nice work, and then I got to know him personally about 25 or 30 years ago, and gradually our wives became friends as well. So it was a great, pleasure to share with him. And I think we both feel the same way and I think most laureates do, that, the one thing to say is that the probability of receiving this award is extremely small. And I think we both feel we were lucky to have it happen, but there's many qualified people, and we more feel like we represented our field rather than our individual accomplishment. But nevertheless, it was a great, real thrill for us to share with my friend Serge. So anyway, with that, I will stop for the final time. And this, of course, these are the people in our lab doing the work.
So thank you very much for that wonderful talk. I think we have time just for a couple of questions from the audience. Are there any questions? Yeah, come on up. There's a mic right here in the aisle, in both aisles.
Hello. Is this mic on? Okay. No? Yes. Okay. I was curious how you keep time on your person. On your person, out and about. How do you?
So
how do
I
you
have
keep
a watch
time?
here, and it's good to about maybe 2 minutes. so not very well.
Thank you.
But probably more seriously, like all of you, I have my cell phone and rely on that these days to give me better time. But.
So another easy question. When you lifted the table up and then moved it back down, did you get back to the same difference of 0?
Yeah, it was reproducible within our precision, Actually, I must say that this was, it was a demonstration, but there's been much more accurate demonstration of this gravitational potential redshift. And I mentioned, I gave a reference when we talked about, compensating for the Doppler shift due to the expansion and contraction of our table. The experiment I quoted there was one where it goes back, it had a rocket which was suborbital. So this rocket went over, I forget where it was launched from, but, went up in this arc and then crashed into the sea. But during this, I don't know, I forget, roughly an hour that it was in this orbit or this trajectory, of course, the gravitational potential changed significantly. Anyway, they were able to measure the gravitational potential redshift to about a part in 10 to the 6, and ours was only, this thing that I showed you was about 10%. So just kind of give the basic idea. And so this rocket on board had a hydrogen maser, actually. And that was done quite a while ago, I think in the late 60s. And that's still the most accurate measurement of the gravitational potential redshift, was this early experiment that was done with a hydrogen maser.
wondering. Yes. Okay. Can't hear myself. What makes an atom a good candidate to be used for an atomic clock?
Okay. I mentioned this briefly, but I mentioned a lot of things. But again, the basic idea has to do with the fact that all atoms of a given kind, as far as we know, are exactly identical. So we have things that perturb the frequency, one being these esoteric things like the gravitational potential redshift. But if we have two atoms that undergo the same environmental perturbations, as far as we know, they should run at exactly the same frequency. And so, as I was trying to make the case there, for example, for a pendulum clock, we have to worry about these things like the pendulum. The length of the pendulum can vary in production, but there isn't that difference with atoms. As far as we know, they're exactly identical. So. Oh, I see. There's no simple answer. In fact, I don't know how many. There's probably 25 different atoms or ions that people consider, and they all have advantages and disadvantages, and some may be good for reducing some environmental effect, and others are better for other reasons. So there's no big winners. So I would say nobody's come up with an atom where this is the choice everybody should be using. One interesting sidelight about that, and what's amazing is that the cesium clock I mentioned was first demonstrated in the 50s, and then about the mid-60s that it was decided it would become the standard for the length of time, the second. And what's amazing to me is it was the best clock from basically the mid-60s till about 2006, where we did this optical clock experiment. So it's just remarkable that it was the best choice for this very long length of time. Of course, they were always working to improve it, but still, it was an amazingly good choice. It was the best clock for that length of time.
So it's getting late, so unfortunately we'll have to end this evening, but I'd like to thank you all again for attending this lecture.
Yeah. Thank you.